All right, we're going to do some more with our beams today. It's raining in the background. Can't really turn that off, so you might get some rain sounds also. But we're going to do these beams. We're going to look at moments of inertia, not just looking them up in a predetermined chart, but also how we can calculate moments of inertia for something like a T-beam like this one that we might have created ourselves. And at the very end, we're going to go through some SolidWorks for if you're in the class, what you're going to do for Lab 1. So that'll be at the very end of the video, though. All right, so let's start with just moment of inertia. So we've done a little bit with moment of inertia, or moments of inertia, whichever you want to say. This is the variable I that goes in our flexural stress equation. At least that's the only place we've used it so far. We could take a step back and look at I is equal to the integral of y squared dA. This looks very similar to an equation we had earlier, maybe y sub c equals integral of y dA divided by a. So if you remember when we derived this one for centroids, this is the y component of a centroid of a shape, then you might remember that we called this the first moment of area. And if you also remember, this came from the fact that we were taking a beam or some object and reducing it to just its cross section. So all you could see was its cross section, like the T here. And we were looking at that area, and you know, that area does represent mass. There's some mass here, and so there would be a force associated with that, and you could think of the moment that that mass creates about an axis. So maybe for y sub c, it's the moment that that area creates about the x-axis. And we called it the first moment of area, just the numerator part, not the divided by a part, but this numerator. This moment of inertia has a similar name, the second moment of area. So you might see second moment of area, and they're referring to the moment of inertia. So what this does, remember, it's in the denominator of our flexural stress equation down here. So when you think of this, the larger value you have for I, the less flexural stress you have. So you can kind of think of moment of inertia in the flexural equation as a large moment of inertia is a less flexible beam. You could think of it that way. So the larger this moment of inertia is, the more rigid the beam is. So we need to find ways to calculate this moment of inertia. We don't have to go and do an integral calculation. We could do this, integral of y squared dA, and calculate the moment of inertia. But most beams are made of relatively standard shapes, like centroids are made of relatively standard shapes. In fact, I've got a chart over here that we can look through. Let's zoom out a little bit and bring it on the screen. There it is. So you've got rectangles, triangles, circles, half circles, quarter circles, and sectors of circles as some of the standard shapes that have pre-calculated. Let's look at just the rectangle for a minute. Moments of inertia. So there's a moment of inertia for a rectangle. Actually, there's two moments of inertia here. There's an IX and an IX prime. Those two different moments of inertia refer to two different axes. Here's the x-axis, and at the bottom of this rectangle is the x prime axis. So that's referring to these two different moments of inertia. It won't really make sense what they're doing until we define a few more terms. But until you're certain of what you're doing with these moments of inertia, you should probably just use the IX. The IX prime can only be used in certain cases. And so if you're not sure of what that case is, you probably should just use the x-axis moment of inertia. So what this is the equation. This is the evaluation of that integral y squared dA for a rectangle, and it's the moment of inertia about the x-axis, which is shown going through the centroid of this rectangle. So each one of these shapes has one of those. It has a x-axis going through the centroid of whatever shape you're dealing with, and it has a moment of inertia about that centroid. And then it has an x prime version also, where the x prime is another axis, usually at the bottom of the shape, but well, this one doesn't have an x prime, but all the others are at the bottom of the shape. So for now, let's just look at this ix equals bh cubed over 12. So what we need to do before we do that, though, is we need to create us a beam, like a generic beam, T. So let's do a T. Not necessarily the same dimensions as this one, but let's put our own dimensions on it. Let's say that this 1 inch from here to the bottom is going to be 4 inches. Let's make this flange. Remember, this is the flange, this is the stem. Let's make the flange a 1/2 inch thick. So it's no wimpy little beam, but it's not some of the size of some of these others that we've dealt with. Make the flange 6 inches, just so we have different numbers everywhere. It's easier to track the different numbers. This can be easily divided into two primitive shapes, a rectangle for the flange and a rectangle for the stem. Before we calculate moment of inertia, we need to know where the neutral axis for this shape is. So we know that it's roughly, here somewhere. But we need to know exactly where it is. So this, remember, the neutral axis is located at the centroid for the composite shape. So this is YC. So we actually need to do that before we can do anything with moment of inertia. So let's do our little table over to the side here to figure out where the location for the centroid for this T-shape is. So we just have two parts. Part 1 is the flange, part 2 is the stem. They each have an area. The area of part 1 is 6 times 0.5, so 3 square inches. 4 times 1, 4. So a total area of 7 square inches. We don't really need to know the location of the x centroid because we could draw an axis of symmetry. We could basically put the y-axis right here, right? So that there's no need to calculate the x sub c. It would just be 0. But we don't know where to put the horizontal axis, the neutral axis. So y sub c for each part. For part 1, we're measuring everything from this bottom. And you don't have to measure from the bottom axis. That's just convenient for me. That's where I drew all my other measurements from. So why not measure that? So I'm looking at the centroid of part 1. So I go up 4.25. Oh, well, I had my units up there. I guess I wrote them there also. For part 2, the centroid, again, it's a rectangle, so I don't really have to go look up where the centroid of a rectangle is. It's just in the center. And this distance would be 2 inches. Might as well write the inches there. Then we need to do a times y, so basically we're doing this numerator. 4.25 times 3 is 12.75. 4.25 times 3, 12.75 inches cubed. 4 times 2 is 8. We sum those together, we get 20.75 inches cubed. Y sub c is equal to 20.75 inches cubed divided by 7 inches squared. That's the numerator is here, the total area is here. This number, 20.75 divided by 7, is 2.96 inches. So that says that this distance from the bottom from our reference up to the neutral axis is 2.96 inches. So we've got that. Now we can look back at our chart for rectangles and get this equation, bh cubed over 12. And why don't I copy this down? So we've got b, the base is the horizontal, the one parallel to the x-axis. H is the height, the one perpendicular to the x-axis. And then we're just going to do bh cubed over 12. So let's copy that down so we can begin to do moment of inertia. Keep this nearby because we'll need it. So here's just a generic rectangle. Ix equals bh cubed over 12. And x is the x-axis that goes through the centroid of this piece. B is parallel to the x-axis, the dimension parallel to it, and h is perpendicular to it. Alright, so that's basically, whoops, we're off the page. That's all I drew. It's just basically recopying the information here. Alright, so what we want for this equation, let's say that we're going to have a beam, and our whole goal is to find the maximum flexural stress in a beam. We don't have the beam yet. Well, I guess, you know, it's this beam. We don't have the loading for it yet. But we'll have to get to that. We'll have to draw a shear and bending diagram to figure out the maximum bending moment. Y, we could figure out where Y is going to be. Just thinking about Y, if we want the maximum flexural stress, and this is the flexural stress, then I want these numbers, M and Y, to be as large as possible to get the largest possible value for sigma. The largest M is going to come by drawing the bending moment diagram. I is going to come from a second, once we finish talking this, we'll go and calculate I for the cross section, and that's not going to change no matter where we are in the beam. And Y is going to be the largest distance that I can plug in for from the neutral axis to some point on the beam. So the neutral axis is, you know, somewhere in the middle of the beam. I could go all the way to the bottom of the beam down here and plug in a number of 2.96. Technically negative 2.96 because I would be measuring from the neutral axis downward. So it's negative 2.96. I could measure from the neutral axis up to the top of the beam, but that is only 4.5 minus 2.96, 1.54. So it's a little bit smaller if I measure from the neutral axis up to the top of the beam. And if I'm trying to find maximum flexural stress, then I want the largest possible value for Y, which is going to be this negative 2.96. So I know that. I don't know M. I don't know I. I know how to get M at least because I draw the shear and bending diagram. But let's calculate this I. So this moment of inertia is the moment of inertia of our beam. Let's shade it in so it's standing out a little better from everything. It's getting too much stuff on it. So here's our beam. And we found the location of the beam's neutral axis just a second ago. And we want to calculate the moment of inertia for the flange about the neutral axis and the moment of inertia of the stem about the neutral axis, and add those together so that would give us the moment of inertia of the T about the neutral axis. What we have here, this equation gives us the moment of inertia of a rectangle about its own centroid. So if I took this equation for the flange, part 1, base of the flange, let's get it on the screen. Base of the flange was the dimension parallel to the x-axis is 6 inches. The height of the flange was a 1/2 inch. This would give me the moment of inertia of the flange, but it would be about this axis, the one through the centroid of the flange. And I want to move that calculation down to the neutral axis for the whole shape. So what I do to make that calculation is I need to add a term here. And I add well, let's just write it in variable form and then we'll plug the numbers in. A times y squared. So this area A, this is the area of whatever part we're dealing with. In this case, it's the area of the flange. So it is 6 times 0.5. You can actually get that off your chart over here if you wanted to. This y is the distance between two axes. It's the distance between the neutral axis of the shape, the T shape. I'm going to abbreviate neutral axis of the T and the centroid of the part that we're calculating. So in this case, the centroid of the flange. So for ours, that is, let's see, what color can we make this? This distance. There's the centroid of the flange. There's the neutral axis. This is the distance y that we need to put into this equation. And that number is 4.25. Whoops. 4.25 minus, so 4.25 is the distance from the bottom up to here. And then we're going to subtract off this 2.96. 1.29 is that distance, inches. What we're doing here is called the parallel axis theorem. So this whole adding on the ay squared, this is the parallel axis theorem. Parallel because there's two axes, the neutral axis and the axis of the part that we're dealing with. And we are making the adjustment that, yes, this flange has a moment of inertia about its own axis, but when the beam is bending about the neutral axis, then I need to take that into account, that this axis, the one through the centroid of the flange, is not at the neutral axis. So that's not the point where it's bending, where the beam is bending about. Remember, the neutral axis is the point in the beam where you transition from compressive stress to tensile stress, or from tensile to compression, depending on which way the beam is bending. But remember, when you bend a beam, so here's a beam. I should have made this one out of flexible stuff that I could actually bend it. Maybe I'll do that next. But when you bend a beam, one half of it's in tension, or not half, one side of it's in tension, and the other side's in compression, or vice versa, tension on the bottom, compression on the top. We haven't put any loads for what this beam has looked like as far as bending goes, so we don't know where it's where, but we know that above the neutral axis is tension or compression, and below the neutral axis is the opposite. And that's where the beam is, it's bending about that axis. So for the flange, if we're doing this for these numbers are for the flange, so let's put these numbers in, and the moment of inertia about the neutral axis of the T for the flange equals, and you don't have to write all these different little subscripts, I'm just trying to make it clearer, equals this term, which is, well, let's write it out in variables. 6 inches times 0.53 inches cubed over 12 plus the area, which is the base of 6 inches times the height of half an inch, times the distance between the two axes, which we said was 1.29 squared. So sometimes this is negative, like when we do the stem, it's going to be negative between the neutral axis measuring down to the centroid of the stem, but you square it anyway, so it doesn't actually matter if it's positive or negative. This should be a plus sign. So this part, 0.5 cubed, is a tiny number, times 6 divided by 12. 0.0625. The units here are inches cubed times inches. So inches to the fourth. Maybe you remember that from looking up moment of inertia from the charts that we used before. This term, 1.29 squared times 0.5 times 6, 4.99 inches to the fourth. Then we add these together. 5.05 is what we'll call it. You could put another 5 in there, 5.055, I suppose. This term is the moment of inertia of just the flange for our T-beam, so just the top part, about the neutral axis, somewhere in there, of the entire T shape. By itself, the flange doesn't do a whole lot. So if we just had the flange bending, flexing about its own axis, it doesn't have a lot of resistance. This is a really small moment of inertia. But then when we move that flange up away from the point of flexing for the shape, the whole shape, we add a lot of rigidity to the beam. And so we get this part here. This isn't the whole moment of inertia for the beam, though. This is just what the flange is doing. We still have the stem adding in. So let's draw the stem. Let's redraw our rectangle in the shape of the stem. And the stem centroid is going to be here. There's our x-axis that goes with the bh cubed over 12. B is still the distance parallel to the x-axis, and h is still the distance perpendicular to the x-axis. So these are our locations for B and H in our equation. So the I about the neutral axis for the stem equals bh cubed over 12, which is b, these dimensions, let's get them. Base of 1, a height of 4. So this is 1 inch. This is 4 inches. Base of 1 times a height of 4, bh cubed. So we cubed the 4 over 12. Plus the area of here, 4 times 1, let's just put 4 inches squared. That's a squared. Times the distance between this centroid for the stem, which is right here, and the neutral axis. So that distance is going to be, well, it's 2.96 from the bottom up to the neutral axis, and it's 2 from the bottom up to here. So this is just 0.96 inches right here. And technically it's negative because the neutral axis is our reference point and we're measuring downward. So it's technically negative. But like I said, we square that anyway, so the negative sign is going to become positive. All right, here we have 4 cubed times 1 divided by 12. So this by itself, 5.33 inches to the fourth, that's more than what the flange is doing altogether. This is just the stem in its normal orientation. Now we're going to add in the fact that we've moved it away from the neutral axis for the beam, for the T, and that's going to be 0.96 squared times 4, another 3.6864. We add these two together and we get 9.01, or 02 actually. All right. So I have two components to the two-piece T-beam. It has a flange and a stem. Flange and a stem. The flange is doing this as far as contributing to the neutral axis of the T. The stem is contributing 9 inches to the fourth. So I would add those together. So the moment of inertia for the T about its own neutral axis is 5.05 plus 9.02, 14.07 inches to the fourth. So this is the moment of inertia that goes into sigma equals negative m times y over I. So that's the moment of inertia that will go into that equation once we get there. But look at a couple of other things here. So these aren't exactly the same shape, right? There's a 6 by 1/2 and a 4 times 1, but they're similar. They're not that far off from one another, but they have very different moments of inertia when it's just them. So the flange is very small. The stem by itself is quite a bit bigger. If you think about that, this could be the flange in this orientation. I know it's kind of close to your camera. It's really easy to bend it this way. So it's really easy to put a load on top and bend it. Same material, same dimensions, but turn it 90 degrees from there and try to bend it. There's no way you're going to bend that. Not with your finger anyway. So you can feel what this moment of inertia is doing here just by orienting things differently. You can see it in the equation. You're cubing a big number here, you're cubing a small number here. And so you can see it in the equations, but you can actually easily feel it just with a ruler. Take the same material, same dimensions, and put the load on a different direction, and it behaves differently. And so that's the same thing that's happening here. So adding this flange on does two things. One, it does contribute to the rigidity just because it's another piece of metal, but it also raised this neutral axis. When, like, just the stem by itself, the neutral axis is down here. But once I put that flange on the top, the neutral axis raises up, and now I've got these two individual pieces, the flange and the stem, that are not at the neutral axis, which adds in this other component to the moment of inertia. So this thing's called the parallel axis theorem. And let's go back real quick to here. This Ix prime, this one, that's at the x prime axis at the bottom here, you cannot use the parallel axis theorem on this x prime equation or any of these x prime equations. Basically, they have already had the parallel axis theorem applied. That's how they were generated. Basically, you took bh cubed over 12 and then moved that down to the bottom of the rectangle in this case. So this bh cubed over 3 was actually created by using the parallel axis theorem, with h over 2 being the distance, the y value. So that's the tricky thing with the x prime. You cannot apply the parallel axis theorem to it. You can only apply the parallel axis theorem to the equations that are at the centroid of the primitive shape. All right. Let's move on to trying to figure out, our real goal is to find the maximum flexural stress. So we've gotten a couple of things. We actually know y now. If we want the maximum flexural stress, y is neutral axis down to the very bottom of the beam is the largest value for y, so negative 2.96. So I know that. I just found I, 14.07. Now I just need m. All right. To get m, we need to know the largest possible value for m in the whole beam. So the way to do that is to draw the shear and bending diagram of the beam. So I'm going to come in and just draw the beam as a line, something like that. Let's put a couple of reactions on the line. So one will be, let's just say it's a roller over here and a pin over here. It doesn't particularly matter what they are. And then let's put a 3-kip load, point load. And then let's put a distributed load over on the, somewhere in the middle of the beam, something like that. And let's call it 2 kips per foot. We're going to go ahead and draw our reference guidelines here. So something like that. Something that marks where the distributed load ends and where it begins, where the point load is, and where this reaction is. And then we can go in and we can add our dimensions here, just so we know how far apart everything is. Let's say this is 3 feet, 2 feet, 5 feet, and 1 foot. So those look reasonable. We don't know these reactions. Let's call this RA and RB. We don't know what their magnitudes are, so we actually need to solve for those first. We would do that by, one thing we could do is summation of moments about A, if we think of this point as A. Now, I'm going to leave the units off in this equation just to not have it squished together over here. So it'll just be numbers in this equation, but I'm going to keep everything in kips and feet. So 3 kips times 3 feet plus, this is a distributed load, 2 kips spanning 5 feet, 2 kips per foot spanning 5 feet. So this is 10 kips total, and this distance would be 2.5 feet. So that would be 10 kips times 7.5 feet, and then minus RB times 11 feet. Those have to add to 0. We can calculate a value for RB. So 3 times 3 is 9, plus 10 times 7.5 divided by 11, 7.64 kips. Now I'm rounding a bunch of these numbers off. So remember, one of the things that happens when you draw a shear and bending diagram is that you start and end at 0. So since I'm doing some rounding, I may not end exactly at 0, particularly on the bending moment diagram. So here I've got RA minus 3 minus 10 plus RB is 7.64 equals 0. Therefore RA is 13 minus 7 point, all this stuff, 9.86. Oh wait, hold on, I did 13 minus pi. 13 minus 7.64. 5, I was looking at those and it didn't make sense. 5.36 kip. There we go. Ignore that. All right, those look more reasonable because they should add to 13. All right, so let's put in our values here. RA 5.36 pointing upwards. RB 7.64 also pointing upwards. Let's draw us a 0 reference line for the shear. I don't know, this looks good enough to me. We'll be in kips. And it looks like we're going to have, we're going to go up, 5 down to 7. So let's make our maximum up here 10. And 5. -5. -10. You just want something that kind of keeps your numbers more or less in scale. It looks like mine are not quite spaced evenly, but it'll be okay. All right. Now we need to start at 0. And then the very first thing that happens is we encounter the reaction at A, which is a point load going up 7.36. So it's a good idea to keep a running total over here in your calculator. So we're at 0. We add 5.36. Gets us to 5.36. And it's a step change. Point loads create step changes. And then nothing happens until I get over here. So if there's no forces, then there's no change in shear. So it's just a straight line across there. And then I encounter a negative pointing down 3 kips. So I'm going to subtract off 3, 2.36. So let's say that that's right there somewhere. And it's this negative step change like that. Nothing happens until I get to the distributed load beginning. So it's horizontal, no change. And then the distributed load is not a step change. It doesn't just go up or down. It's a gradual change because I'm gradually adding more and more force. You ignore the 10 kips, right? That's not even part of it. I just used that to do these calculations over here. So it's just the 2 kips per foot. I guess the 10 kips does play a role because I started at 2.36. And then by the time I end the distributed load over here, I have lost a total of 10. So 2.36 minus 10, 7.64, negative 7.64. So in here. And since this is an evenly distributed load, or a say constant height here, then I have a constant slope here, which is just a straight line. Now it's certainly possible to have any shape, curve or triangle or whatever you might have over here. What that does is that means that this isn't a straight line. It is changing at the rate that this is changing. So you would have some kind of polynomial in this. For this course, we're just going to use evenly distributed loads whenever we're doing beams in bending and drawing shear and bending diagrams. So it will always be a distributed load will create triangles, basically. Then there's no change until we get to the very end of the beam, which has a positive 7.64. We're at negative 7.64, so that gets us exactly back to 0. So that's a good sign. Although getting back to 0 on the shear diagram doesn't necessarily mean you did everything correct. You could have just calculated these wrong and it still worked out. Getting back to 0 on the moment diagram pretty much means you did everything correctly. So let's shade this in. You don't have to. I just like doing it. Well, we'll leave it like that. All right. Now, sometimes you have concentrated moments on the beam that will affect the bending moment diagram. But if you don't, then the bending moment diagram is completely determined by integrating the shear diagram. To integrate it, you calculate the area, basically the area I've shaded in here, which is a bunch of rectangles and triangles. So there's a rectangle, there's a triangle, there's another triangle, and a rectangle. So the rectangles are easy. Height, what have I got going on there? Don't know. 5.36 times a base of 3. This is kip feet, so that makes sense for a moment, kip feet. 16.08. 2.36 times 2. This area is 4.72. This one, we know the height, 2.36. We don't know this base, though. So we have to do a little bit of extra calculation to figure out this distance. And once we figure out this distance, we also can figure out this distance pretty easily. All right, so how you do this is, if you know the height, the other thing you know is the slope of this line is negative, because it's pointing down, 2 kips per foot. So m equals negative 2 per foot, 2 kips per foot. So if I'm at 2.36 and every foot that I go over, I'm losing 2 kips, all I need to do is divide by 2, and that will tell me how many feet, 1.18, how many feet it takes before I reach 0 from 2.26 at a rate of negative 2,000 pounds per foot. And once I know this 1.18, I can take 5 minus 1.18, 3.82 for this distance. Oops, 82. Wow. That's an 82. Hopefully we'll remember that. It's kind of hard to read. Then I calculate this area. It's still positive, still above the 0. So it's 2.36 times a base of 1.18. But it's a triangle, so don't forget, divide by 2. 1.39. Look, there's some decimals I'm going to leave off. So it's going to throw off my moment calculation a little bit. Here we have a negative 7.64 times a base of 3.82 divided by 2 because it's a triangle, 14.59. And that's a negative one. Let's put it down here. Negative 14.59. And then this last one, well, it's times 1. So negative 7.64. Okay. Now what we would do is we would also make sure that we took into account any concentrated moments, but this beam didn't have any external concentrated moments. I would go in and mark where this point is, just as a reference line also, just so I don't forget that it switches there. And it that's where the peak is going to normally be. Wherever this thing transitions from positive to negative is usually the peak of the beam. It depends on the loading, but a lot of times that's the peak, so I want to mark that out. I want to draw a reference axis for the bending moment. I want to put it way at the bottom because the way this beam is loaded, it's pushing, all the loads are pushing down, which is, I don't know exactly how, what shape, but it's going to be more or less bending with tension on the bottom, compression on the top of the beam with these loads on it and those supports. So if that's true, then that's a positive bending moment when tension's on the bottom. So I'm pretty sure there's no negative bending moments, nothing that's causing the beam to bend with tension on the top. So I can move the reference for pretty far down to the bottom. If I thought there were sections of the beam where it had tension on the top, then I would move this higher up so I could draw down beneath it. We've done our integration. Now let's start at 0. Reset our calculator to start at 0. And the first thing that happens is we have a positive shear, so that means a positive slope going upwards. It goes up by amount of 16.08, so plus 16.08. We were at 0, so it goes to 16.08. Oh, we need to put our markers on here. Let's see. Let's say that our max wants to be right in there, and it needs to go up to 25. So we can do, wow, I should have done a easier to divide number. So let's say that there's 20. I don't know if this is going to work out. 15, 10, that's pretty close. 5. Not bad. All right. So 16 16.08 is somewhere in here. Now we just have to decide, how do we connect these 2 points? Is it a straight line? Is it curved somehow? And that comes from the fact that our shear is constant in this section. So that means our slope is constant in the bending moment diagram. And a constant slope is a straight line. So like that. And then I would mark down that this is 16.08. Okay. Then we add, this is positive above the 0 reference line, so add 4.72. Now we're at 20.8, which is, you know, maybe right here. 20.8. And again, I have to decide how to connect the 2 dots. This is a constant shear, so I have a constant slope. So another straight line. It has a different slope, but there's also a different shear here. So it does make sense that this slope is positive, but at different angles, because there's more shear here than there is here. So this is a steeper slope relating to the more shear. This one's also positive. It adds another 1.39. So we're going to max out at 22.19, right in here somewhere. This one is not a straight constant shear. It's actually a decreasing shear. So that means I have a decreasing slope. It's still positive, so it's still generally upwards because this area is above the 0 line. But it's going to curve. You know, I can't even really draw the amount it curves because it's such a tiny section. Maybe there'll be more curve in this next one. So we're at 22.19. Now we subtract. This is a negative 14.59. And that brings us down to 7.6, which is somewhere in here. Now these are negative. I do a couple of things. I write, when I'm doing this areas, I usually try to put the areas when they're positive above the axis here, and when they're negative below the axis, and also include a negative sign to remind me that, you know, I'm subtracting away from the moment diagram. This one starts at 0, so that's a horizontal slope, and it gets more and more negative, which means the slope gets steeper and steeper. So it's going to do something like this. Something like that, some kind of curve. It's not a straight line between those points. Here, I'm at 7.6. I'm told to subtract off 7.64, so I actually end up pretty close to 0. I'm going to call it 0, but it's actually off by 0.04. I think that's okay. This is a constant shear, so I have a constant slope, which is a straight line. Now, there should be continuity between this curve and this line, but that's okay if it looks a little bit crooked. But it started and ended at 0, so I think we've done everything correctly. I do like shading them in, although it's totally unnecessary. All right, but here is what we were looking for. We were trying to find the maximum moment, which we have found to be 22.19 units of kip feet. So now we have sigma equals negative m times y over I. M negative 22,190 foot-pounds. Those feet are going to mess up with the inches in the y and I, so I'm going to convert 12 inches per foot. So now it's in inch-pounds. There is a negative in front of it because of the negative sign in the equation. Y is, we're trying to find maximum flexural stress, so we need the maximum possible value for y, which would be neutral axis down to the bottom of the beam, negative 2.96 inches, and then divide that by the moment of inertia for our beam T-shape, which was 14.07 inches to the fourth. So all of this will tell us the maximum flexural stress in our beam, and it will be 22,109 times 12 times 2.96. The negatives cancel each other, or they become positive, divided by 14.07. Oh, that's a big number. All right, sigma max is 55,814.6 psi. So 55.8 KSI. So that's a relatively large number. We'll have to look at some charts to see how bad it is. But it might be, depending on what material we choose to make our beam out of, it might be that it would actually, it wouldn't fracture most steels, but it would certainly yield some steels. So this stress exists, if this is our beam, then we go over 6.18 feet from the end. So we go over 6.18 feet, somewhere right in here. And we go to the bottom of the beam because of where we put Y. So right at that point on the bottom of the beam, 6.18 feet from the left end, that's where this stress exists. It's a positive stress, so it's a tensile stress, trying to pull the beam apart right at the bottom of that stem over there. Let's look and see how bad that is as far as material strength goes. That won't help us. That will help us though. So here are tensile strengths, elastic strength. So these are yielding strength. If I exceed this number in PSI, or this is KSI, if I exceed this number in KSI, which we're at 55.8 KSI, then I have permanently yielded the beam. If I exceed this number, the ultimate strength, I have fractured the beam. So this, now you wouldn't really make a beam out of wrought iron, but if I did, I would have broken that one. And I would have yielded all but the hardened 0.2% carbon beam and the hardened hot rolled 0.8% carbon beam. Those would have been okay. Even the hardened one here is pretty close. We're at 56 KSI, and it's 62. So we don't have a lot of factor of safety, but we have some. So that would tell us that this beam is pretty close to loading at its maximum loading capacity. Now, one of the things we're going to do soon, actually Wednesday, we're going to do more of this. We're going to do more of, this with basically more complicated loadings and cross-section type stuff. But I think on Friday, or at least soon, not Friday, Thursday, we're going to do how do you pick the right beam to handle this loading with a given factor of safety. So we'll look at how to do that later so that you don't have to just kind of iterate over and over. There's a much simpler way, assuming you're using standard beams in a chart somewhere. All right. Now the next thing we're going to do is we're going to look at SolidWorks. Find it right here. Oh, you know what? I don't know if I have. Let's see. Will this bring up SolidWorks? Nope. That made a crazy thing. There was SolidWorks. So let's see if I can get this to fit right. There. That'll do for. Well, no, you need to see some of those menus over there. So let's move that over a little bit. And you might need to see this side too. That'll work. All right. So what we're going to do, this is if you're in the course, or if you just want to see a simulation in SolidWorks, then we're going to create a finite element simulation of a tensile test specimen like we would normally do in class. So normally in class we would go in and actually cut out, laser cut little wooden tensile test specimen for the truss that we would build, and you would take one and you'd put it in a testing machine and tear it apart to see how much force it could hold. We can't do any of that online, so we're going to simulate some of that. So first we need to build a part though. Actually, I think I already have a new part here. We just need to build it. So these tensile test specimens, so if it was a metal, like for one of the ones we just looked at in the chart, you would probably have a round tensile test specimen that would bolt into a really large machine. What we're going to do here is a flat specimen, and it's not going to be that big. We will make it out of metal just because the simulating wood or a material that's anisotropic, something that doesn't have the same mechanical properties in all directions. It's a little bit complicated beyond what we need to do in this particular course. So we're just going to do a flat dog bone shape steel specimen. So here's how I'm going to build the shape. It's going to come off the center, and we'll dimension it in a second. So I'm just going to give it some rough dimensions right now. Something like that. Let's close that shape so that it's 1/4. This is just 1/4 of the shape. Let's dimension this to be, this thing is probably, when we cut these out in the course, this is probably 1 inch. So let's make that 1/2 inch. Let's make this, this is the little tab that would mount into the machine. Let's make it 1 inch long. This is half of the gauge length of the material. Let's make it 1.5 inches. And then this little corner right here with this right angle is generally not what you want. So let's fillet that. Let's make it a larger. Let's make it 1/4 inch fillet. Oh, it should do a, well, no, I didn't actually specify how thick this was. Hold on. Let's make this, oh yeah, that's way too thick. Let's make this, this is half of the width of the thing. Let's make it 0.125 so that the whole thing ends up being 1/4 inch thick. There we go. Now we can fillet our corner here and make it 1/4 inch fillet. All right. So let's, this is 1/4 of our model. You could even fillet this corner if you wanted to, just to reduce the stress concentration over there. It's not a big deal. Can't be that big though. Probably be bigger than that. No, guess not. Ooh, can't be that big. There we go. Just a little fillet on that corner. All right, and now we're going to take this model and we will mirror it. We'll mirror it about here. And then we'll take this model and mirror it about here. All right, now I've got relations everywhere here. I have some extra things. I want to trim these out in the middle. It doesn't like me trimming some of that. I can't even see what's going on in there. There's so many things. I don't need this though. I don't need that line in there. It's fine. All right. Now I've got a bunch of relations and a couple of dimensions. That looks like our generic dog bone shape. Doesn't like something. The sketch not a zero length line. I don't know. We might have to deal with that. Let's make it a 0.125 inch thick specimen. And there we go. So this specimen would mount into a machine. Sometimes we drill holes or cut holes if it's laser cut to actually bolt it into a machine, or you have grippers that would clamp on either end here to clamp into the machine. But this is a decent specimen. So it's got a 1/4 inch wide by 1/8 inch thick gauge area. And then these flanges, they just need to be bigger. So we made them 1 inch by 1 inch, basically squares with some fillets on them. And then we made the gauge length 1.5 inches long. No, 3 inches long, 1.5 inches for half of it. All right. I like perspective on. Now let's take this into simulation. So we have this simulation tab. If you don't have the simulation tab, then you need to go to Tools, Add-ins, and check it so it will boot up. You may have to reboot to make it install. I don't know, or reboot SolidWorks. I think it actually will do it on its own without having to restart SolidWorks, but this has to be checked. And then you'll have the simulation tab, and we're going to do a new study. And the study is going to be static. We're not going to do anything super fancy, so this is going to be just a static study. Our part, we need to add a material to, so I'm going to right-click on part and apply edit material, and it gives me a lot to choose from. I'm just going to do a 1020 steel. You can use whatever you want, but 1020 steel is a good generic. You should notice the material kind of changed color, representing that it's got a material property associated with a color now, or vice versa, a color associated with a material property. You may not notice that or not, because it doesn't change a lot. Now we're going to fix one end of this. So I'm going to right click on fixtures, and I'm just going to make fixed geometry. And I'm just going to go in and say that this bottom surface, see these little green arrows? These little green arrows are saying that this bottom surface now is fixed as far as the simulation concerned, so it doesn't move. And the way, if this were our tensile test specimen, what we would actually do is we would clamp it in the machine, and the machine would start pulling it apart. So I'm going to do a similar thing. I'm going to add a displacement to the top up here. So that's in external loads, right click, prescribe displacement. And I'm going to put the displacement on this surface. And I'm going to choose the direction. So this pink box over here is what direction do I want it to displace. I'm just going to pick one of the vertical lines. So here's one. And I'm going to use a millimeter. Well, what is, oh, I put the edge in the wrong thing. Oops, hold on. Edge needs to go in the pink box. There we go. All right, so these little arrows, now you can see they're pointing down. So I actually want it to pull apart. So it'd be a tensile test, not a compression test. So I'm going to put a negative in for the direction here in the, the millimeter translation box. And let's just do 2 millimeters. So not too far, just a little bit. 2 millimeters. Don't want to do that. -2. And check. And when I put the negative and check, confirm it, then you can see the arrows going the way I actually want them to go. Okay, so I've got a force that's pulling this up. Now in the machine, there's a crosshead that moves upward, and you measure the force. So that's why I didn't apply a force. This is more like what the machine is actually doing. It's applying a displacement and you're measuring the force. We're not going to measure the force. We're going to actually just calculate the stress here. So we're going to right click on mesh and mesh and run. Hopefully it'll run with this error still in it. Looks like it did. All right. So now you can see our really high stress concentration at this fillet. That's where our highest stresses are. So we might even have to make a larger fillet, a better transition between here, because we really want these things to break in the center. You can also see if I hover over it, that orange outline, let's zoom in. That orange outline, that's the original shape. And then the colored one is the exaggerated but deformed shape. So it's exaggerated by a factor over here. It's telling me of 6.35. So it doesn't actually look like it stretches that far. In fact, it's supposed to stretch 2 millimeters. And so it's actually exaggerating what it looks like, just so you can get an idea of does it look like the right kind of thing I expect. Let's right click on results and do a factor of safety plot and see if we have anything that's still safe for this material. We're just going to do it on all. Well, not really. It says that there's not so much stress in this corner, but where we expect the thing to break, it says that yes, it would have exceeded the factor of the yield strength of the material everywhere. So we would have to either displace it less than 2 millimeters to create a safer one. But if you're doing a tensile test, then you actually are trying to pull it apart. So you do want it to stretch and then break. So we could get an idea of the stresses that are in it. If we wanted to, we know this area, right? This area was 1/4 inch by 1/8 of an inch, 0.25 by 1.2 or 0.125. If we know the stress and the area, then we can calculate what force would be in here also. But at this point, we've actually exceeded the strength of the material, so it wouldn't necessarily be able to hold that material. I don't know if it calculates a limit or not. I think it just calculates what, assuming it doesn't break, this is what stress would be. I want to show the stress plot again. There it is. So it looks like the stress in there is in the darker yellow, so around 4-ish something times 10 to the 9th. But our yield strength is 3 times 10 to the 8th, according to whatever they've got material assigned to the, I think I did 1020 steel. So we would have to go in and modify this displacement. So we did 2 millimeters. Let's do 1 millimeter. Now it has to rerun. Notice the little yield signs here saying that those results don't apply anymore. So you have to mesh and run again. We're still in the, times 10 to the 9th range for most of these stresses that are saying that this is going to fail. And if we did the factor of safety plot, you would see it basically all red again, except for those corners again. All right. But that's what I want you to do. I will, if you're in the course, I'll write it up for what I actually want you to turn in. But this is more or less the steps to get to the what I want. So you can always go back and reference this. It's also if you've never done a simulation, a static simulation in SolidWorks, it's a good intro to a simple thing. The geometry is simple to do. These fixtures and displacements are simple to do. Instead of a displacement, you could apply a force, and it would give you the same type of thing, except you would know what force is applied. You would be able to get the similar plot. Okay, on Wednesday, we'll do basically another sample of, if I can get all these screens off, one of these. We'll just start with more difficult cross sections than the T that we did here. I can't find, here it is. So maybe we'll have something a little bit more difficult there. And maybe we'll add a couple more loads to deal with here. Or maybe we'll do a cantilever beam. We haven't done a cantilever beam shear and bending diagram. So it'll just be more of the same thing with a little bit more detail. I don't think we'll have to introduce any new things for Wednesday. All right, but I will see you then. And let me know if you have questions. Let me know if there's some other example you'd rather see, but that's my plan, is to do another one of these, and I'll see you on Wednesday.